A BCA table is another way in chemistry that we can keep track of what the limiting and excess reactants are, but it also tells us how much of the excess reactants are left over. So this is an alternative way to solve a stoichiometry problem with limiting reactants without actually setting up the dimensional analysis and canceling units out to do the stoichiometry. We're going to do this in a very narrow context, only with acids and bases. It can get harder, but the context here is all these coefficients are 1, and they all represent moles. So we're going to fill this chart out with some numbers, and all of those numbers need to be in moles because we're comparing these mole ratios. What that means is when we have an initial amount of moles, let's say 0.15 moles of acid and 0.25 moles of base. I'll just erase the moles. Everything in here is going to be moles. This gives us now a way to compare them and see which one's going to run out first, because all the coefficients are 1 and we can compare them. Now, we don't typically get these numbers here in moles. There's 2 ways we would get these numbers. Sometimes you would get them in grams, or sometimes you would get them in molarities and volumes. And if you had either of those 2 cases, you would need to calculate the number of moles before you can put them in this chart. So BCA stands for before the reaction. If you want to write that down, before the reaction, the change, and then after the reaction, how much is left. Because acid-base chemistry is going to deal with a 1-to-1 ratio, all of these coefficients are 1. The story is the same. 1 hydrogen moving. This 1 hydrogen and 1 hydroxide make water, and we make a salt. We know that for every one of these, I'm going to say 1x, one of these is going to be formed. And then, we have no products yet because this reaction has not taken place, so 0 moles of product. But I'm going to gain x amount of my products as well. Now, you can imagine if we did a different balanced equation with coefficients, sometimes our mole ratios were 2 to 3, 1 to 2. That really makes this a lot harder, but we're not going to do that in acids and bases. So watch what happens here. Since these are in moles, we can make a direct comparison, and we can just physically examine them now. We can see that I have less moles of acid than my base, so my acid is going to run out first. You couldn't do this with grams. You cannot do this with molarities and volumes. You can only do it in moles, so we set this whole thing up in moles. But if I know that I have less acid, this is going to go away all the way to 0. I now have my value for x. X is 0.15. So this is going to lose. It's a 1-to-1 ratio here. If one of these takes one of those, if I have 0.15 of this, 0.15 of this is going to go away as well. So now I've got 0.10 left over. Because I have less acid, that makes this my limiting reactant. And it tells me that my limiting reactant means I'm going to have an X value of 0.15. That means I'm going to make 0.15 more water, and I'm going to have 0.15 moles of sodium chloride. And remember, these are all in moles. So it doesn't totally answer our question right away, but it does tell us a lot of things all at once. It tells us because the limiting reactant drove all of this, it tells us how much product we can make of each chemical, and it tells us how much excess reactant is left over, and that's a new powerful thing. So that's a really good thing. And then depending on the question that's being asked, we can use this chart to answer a lot of questions. We could say, how many grams of salt did we make? Well, we could use the molar mass to figure out how many grams that is. We could say, what's the molarity of the hydroxide that is my excess reactant? Okay, so this is excess. And moles divided by liters, here's my 0.1 moles. If I had moles divided by liters, I could get a molarity. Now, this is actually the one that's going to be really important for acids and bases, because we are interested in having an acid or a base left over, because we can use the excess reactant to tell us what the pH of the solution is going to be. If I have excess hydroxide, NaOH, we know that that's a base. So this is going to give us a basic molarity, but we have to know the molarity to calculate the pH and confirm that it's basic. So this is how a BCA chart sets up. It's got a couple of different steps. Number one is, depending on what you're given for your balanced equation, you have to write the balanced equation, convert your molarities and your chemicals into moles so that you can put them in this before line. Then you would have to see which one is going to run out first to find out your limiting and excess reactant. And then your limiting reactant, that X value, kind of fills in the rest of this chart. And then afterwards, depending on what your question asks, you could use these numbers to continue to do some chemistry and answer molarity questions, pH questions, or mass questions of your products.